All right, it is Monday and we are back, I guess. November 16th, chapter 12. We're in the middle of chapter 12. We actually started chapter 12, the reduction part. We'll do a little review and we'll mix in some oxidation reactions, see how many people read ahead here in a minute. So we'll have a little in-class group quiz maybe. But homework 12 will be due tonight. We will finish it. We'll finish the oxidation part. Quiz 7 will be on Learning Suite shortly. I don't think it's on there yet, but that'll be due tomorrow. So it'll be over this chapter 12, some of the reactions there. Chapter 13 is coming up. We'll start on Wednesday, and that begins the spectroscopy part of our course. We'll look at IR, infrared spectroscopy, and also mass spectrometry. IR will tell us functional groups, mass spec will tell us the molecular weight. Very good information to figure things out. But then the big one coming up is chapter 14, NMR. That will tell us connectivity. So we'll see how we determine structures in OChem. Very important topics. We're still grading test 3. We'll get that back as soon as we can. There's no scores on Learning Suite yet, but look later in the day, and if you see the score, it'll be back in the slots there. But I saw a number of really good scores for multiple choice, so I know it's good, and I've talked to a couple students who felt like they did very well, so that's good. Anything else on the business end here? I think next week, Thanksgiving break, we'll have Monday and class on Tuesday, which will be a Friday day. I'll say more about that. And then after Thanksgiving, we were just talking about that, we'll be all online. Okay. And then we still have that midterm 4 coming up. Well, I'll talk about grading results on Wednesday. Let's go to the overhead here, Colin. The outline for chapter 12, oxidation and reduction. We started out with the reduction reactions here, hydrogenation reactions of alkenes with palladium catalyst to go to alkanes. You can hydrogenate carbonyls to go to alcohols. So those are reductions. Remember, reduction in OChem means adding hydrogen and or taking away oxygen. You see here, clearly here we're adding 2 hydrogens, right? We talked about a little application of fats, polyunsaturated fats, partial hydrogenation, or complete hydrogenation to go to saturated fats. We also did alkyne hydrogenation. With the active catalyst, it goes to alkanes. With the poisoned Lindlar catalyst, and all you need to say is LIN there. You don't need to draw out this whole mess. But you have to have the hydrogen there. And then the poison catalyst, you go to the cis alkene product, which is just 1 syn addition to 1 pi bond. Okay. To do the next one, to hydrogenate the next one, it just can't fit onto the palladium because it has all these other things bonded to the palladium. So it slows down the second hydrogenation, which is very fast with a normal catalyst. And then we had the complementary trans product here, the trans alkene, which is generated from the alkyne using sodium, metal, and ammonia. Then we had a little on LAH, reacting with alkyl halides and opening up epoxides. With oxidations here, we're going to be cleaving the pi bond again and adding carbon-oxygen bonds, forming epoxides or diols or cleaving things. And so here's the reactions today. We'll look at epoxidation with a per acid. This is a peracetic acid, or we can use MCPBA. The bigger, more convenient reagent stands for metachloroperbenzoic acid. And there, if you have a cis alkene, you go to the cis epoxide, or a trans alkene, you go to the trans epoxide. Very important reaction because we've already learned that epoxides are very useful for synthesis, right? You can functionalize 2 carbons at a time. It's electrophilic. You can add different nucleophiles to it or open it up under acidic conditions. So these epoxides are very useful. We'll show you an application of that. Dihydroxylation, the new reaction here is osmium tetroxide to go to the cis or syn diol, which is complementary to opening up an epoxide before just with base. and this gives the trans diol. And then molecular scissors is ozone, O3. You've probably heard about the ozone layer in the upper atmosphere, maybe, that protects the Earth from damaging radiation. We can generate ozone with an electric arc with some oxygen gas. Then we pass an alkene through that material. It'll form an ozonide, cleaving both the pi bond and the sigma bond. The ozonide, and we'll show you how that generates here, breaks down with dimethyl sulfide or zinc. Sometimes if you leave that off, we'll still give you credit there. Just show ozone, molecular scissors, and then stitch in carbonyls on both sides. So if in this substrate, it would go to a ketone and this aldehyde here. You see there's a hydrogen right there, right? So yeah, ozone, very good reaction there. And then alcohol oxidation's primary with chromic acid goes to carboxylic acid. Secondary goes to a ketone. Pyridinium chlorochromate, PCC, sorry about the acronyms, that stops primary alcohol to the aldehyde. And maybe we'll talk about the breathalyzer and Mother Nature's oxidizing agent, NAD+, and the asymmetric epoxidation, the sharpless epoxidation. So there's quite a bit in here. I think there's 8 total new reactions. So another reaction heavy one. But we only have one other big reaction chapter coming up. That's 15 with the radical chemistry. 13 and 14 are all spectroscopy, so no new reactions there. So you can take some solace in that, I think. Let's go over here to the board and see how we do on this in-class group quiz. No, it's not graded, don't worry. We just want to gauge your recall from last time and to see if you've read ahead a little bit. And we kind of summarize these reactions already, so you can already kind of predict some of these products here. But this is the important level of understanding of OChem, right? First is always structure. Second is always reactivity. What combination of starting material and reagents give what product? So what do we see here? Hydrogen, palladium, that's the active catalyst, right? There's nothing else bonded to the palladium. And it will give what? The alkane. We don't draw the new hydrogens. You should recognize the pi bond's gone away. We've added the 2 hydrogens there. Same thing here. We now have a tetrasubstituted alkene. And here, the stereochemistry of where these 2 methyls end up. Are they cis or trans? Maybe we'll poll the class. Do they end up cis? Who says cis? Yeah. Okay, most people say cis. And that's because it is syn addition. We showed you a little bit about the mechanism, but these 2 hydrogens come in from the same face because the palladium coordinates the alkene and delivers the 2 hydrogens there. Okay. So again, the alkane, but there you can see some stereochemistry. Okay. You don't always see it. Here, the stereochemistry doesn't matter. Okay. But here it does, often on these cyclic ones. How about with an alkyne with hydrogen and palladium? Again, that's the active catalyst. We assume excess of the hydrogen. So what are we going to go to? We're going to go to the alkane again. And here we had 2 equivalents of hydrogen, right? So with the active catalyst, alkyne to alkane. Okay, it'll fully hydrogenate. But if we have the Lindlar thing, and this is the palladium with the calcium carbonate, lead tetraacetate, and quinoline, there's actually a lot of variations of the Lindlar catalyst. You can either draw them all out if you want to, or just say Lindlar, okay? But show the palladium, and this is implying those other ligands, those other groups are on palladium, which slow down the second addition. So hydrogen here with that alkyne, what are we going to go to? Yeah, we're going to stop at the cis product. Now make sure you draw cis there, okay? Because that's part of the stereochemistry. You kind of see it here with the syn addition of the 2 hydrogens here on this tetrasubstitute alkene. But with the alkyne, it just adds once, and then because of the ligands on here, adding the second time, it's harder to coordinate. It's easier for the palladium when it's poisoned to coordinate the linear alkyne. Not going to get into the mechanism a lot there, but that first addition to an alkyne is fast, okay? If you blast it and heat it up and pressurize it, you can get the Lindlar poison thing to actually go to the alkane. But preparatively, what we're interested in is stopping at the cis there. That's the useful thing, okay? And then we got the complementary sodium in ammonia reaction, and that will give the same alkene but with what? Now trans geometry. We did go into the mechanism there. Check the class video out from last time. It's a 1 electron at a time addition, and then you protonate the vinyl anions here. So actually you have to have excess, at least 2 equivalents of the sodium metal to do that, but I've never put that mechanism on a quiz or a test. The reactivity is the important thing here, I think, okay? So make sure you understand that part at least. All right, now let's see who read ahead and can handle this, or at least look at the general outline there and see. MCPBA stands for metachloroperbenzoic acid. We'll write that out in a second here. And this is with a cis alkene. So we're going to form what? An epoxide. And that epoxide is going to stay cis. Okay? It's a stereospecific reaction. The oxygen from the per acid lays down on one face or the other, top or bottom. Those are stereocenters, so MCPBA is achiral, the starting material is achiral, so actually we get a racemic DL mixture, the 2 cis ones, okay, not the trans ones though, okay. We'll see from the mechanism, we'll show you the mechanism there. They've got osmium tetroxide here with that alkene, and what are we going to get? We're going to get the alcohol there and the alcohol there. We still have this methyl group in the back there, but the 2 alcohols from the osmium tetroxide, that's osmium in the formal +8 oxidation state. That's a transition metal, okay, in the late series there. You can see it's in the 8th row over, so it can have 4 oxide 2- ligands on it. When it reacts with alkenes, it forms the cis products there. And again, that's DL because it could come from the bottom also. And here's ozone doing its thing, and it's going to form what? Ketone here, molecular scissors, snap apart both the pi bond and the sigma bond, and we'll have an aldehyde here. So count carbons there, that's kind of the tricky thing. But this became a ketone because it was a methyl group up here, and this because of the hydrogen right here stays as an aldehyde. We'll see some of the mechanism of that one. Chromium, this is chromic acid, this is CrO4, H2. Very strong acid, similar to sulfuric acid, its pK is very low. But this is a redox active transition metal. Chromium's the 6th row over. It can be in the +6 oxidation state. But chromium can be in different oxidation states. Actually, it will oxidize the substrate here. And the primary alcohol will go to the carboxylic acid, and the chromium will actually go to chromium 4 oxidation state. And here's the breathalyzer test. So law enforcement used to use these little tubes before they had the IR-based test. These little tubes had some high oxidation state chromium in it. And when you breathe into the tube, what? They're looking for ethanol on the breath, right? For people being drunk driving, whatever. This starts out as red in color, bright red, the higher oxidation state of chromium. When the alcohol gets oxidized to carboxylic acid, the chromium goes to a lower oxidation state. Redox often goes together. Something gets oxidized, something gets reduced, because the electrons have to be kept track of, right? So this actually turns out to be greenish blue in color. So law enforcement used to look at the color change in this tube to estimate what level of alcohol is in the breath. Of course, there are other things to follow up with that, but that's the so-called breathalyzer test, the old one anyway. The new one's based on IR of the infrared spectra of ethanol. Okay, here's the other reagent, PCC pyridinium chlorochromate, and that will take primary alcohols and stop at the aldehyde stage. Okay, so we say those are complementary oxidation reactions. This one goes all the way to the carboxylic acid, and it has to be a primary alcohol to go carboxylic acid. Secondary alcohols go to ketones, okay, with both these reagents. But primary alcohols will go there. And then tertiary alcohols, no reaction, okay? We'll show you a little bit of the mechanism to figure those out, but you're okay. How do you do on the quiz so far? Those last few maybe a little tricky there, but yeah, so there's 8 or so new reactions here. Let's put on the board all the oxidation reagents that we're going to talk about. So oxidation reagents, what? Are going to have a lot of oxygen on them because they have the ability to transfer those oxygens to substrates, okay? So this is peracetic acid. You see the peroxy linkage there. And you're probably more familiar with peroxide itself, okay, the bleaching reagent. But you see the peroxy link here in the peroxy ones. And then we got MCPBA, which is this guy. It's got a benzene ring, and it's got a peracid. So MCPBA is similar to peracetic acid. In fact, all the peracids will do epoxidation reactions. The nice thing about MCPBA is it's a well-behaved solid material. We can weigh it out. It's not corrosive. We can get the right equivalents and add it in conveniently. So we often use that. The aromatic thing, and then the byproduct is the carboxylic acid itself, and that's easy to separate. Okay. Peracetic acid's okay, but it's hard to get it in pure form. Okay, it's a solution. It's a little bit harder to handle. And then we got the chromium reagents. Chromium oxide is a very dangerous reagent. That's in the oxidation state of what, +6 here. Remember, oxide ligands are 2- ligands from Gen Chem. There's 3 of them there, so chromium's +6. And a lot of oxygens that can transfer that. And then we have chromic acid. Let me draw out the whole structure for that. So chromic acid is H2Cr04. That looks like sulfuric acid. Sulfuric acid is not an oxidizing agent. It's a strong acid. Chromic acid, you can see the conjugation here, the conjugate base would be resonance stabilized like sulfuric acid, but it's redox active now. The chromium can change oxidation states, okay? So it's a little bit different there. We can make this different ways. We can make it from sodium chromate and sulfuric acid, okay? In fact, you see a lot of ways to make sulfuric acid. You can also make it from potassium dichromate, and this is a bigger structure to draw out. There's 2 chromium oxides stuck together. But this is a salt form. But again, if you react it with strong protic acid, you go to chromic acid. And that's really the actual oxidizing agent for the alcohols. So yeah, that's a good one to keep in mind. And also potassium permanganate. Manganese in the high oxidation state. This is the purple oxidizing agent. Again, all of these, what do you see? A ton of oxygens on them. So they have the potential to transfer that oxygen. Same thing with osmium tetroxide. 4 oxide ligands here. So yeah, +8 oxidation state. That's OS, osmium. Okay, that will do the dihydroxylation reaction. And then we got PCC, pyridinium chlorochromate. Let's draw this out. Pyridinium is actually the protonated form of pyridine, and then the chromate is actually this, where we got the Cr, Cl, OO, and O-. Chloro, that's what this C here is. Pyridinium chlorochromate. It's chromate, but one of the oxygens has a chloride on it, okay? And it's deproton over here, but it still has a lot of oxygens, can still do the oxidation. But this is a nice non-acidic now reagent that can do the oxidation of primary alcohols to aldehydes, but it's not acidic like these guys here. These are the aggressive ones. These go all the way to carboxylic acid. PCC will stop, and you can already see why. It's not acidic now. Well, it's got a very weak acid. The pKa of protonated pyridine is only about 5. Whereas chromic acid here is what? -3. Okay, very strong acid. So I think it's good to have them all up here. And then we'll see NAD. NAD+, which is the cofactor in biology that does oxidations similar to some of these inorganic oxidizing agents. Okay, so that's all of them. It's good to have them all up there. Let's look at epoxidation first. So what are we doing here? Well, we're adding peracid to an alkene, and we can do peracetic acid. Remember, there's two oxygens there. And what do we go to? We go to the epoxide. Here, the stereochemistry doesn't matter. It's an electrophilic reaction, so the more substitute alkenes are faster. The reagent here is actually electrophilic. We're going to break this oxygen-oxygen bond and form acetate. We'll see the mechanism, how this will work. But more substituted alkenes actually react faster. A slower reacting one would be this one, where we go to the DL pair here. That is a stereocenter right there, okay? So monosubstituted ones. If you look at ring alkenes, stereochemistry, it's cis here, okay? This one's achiral. Those are not stereocenters because of the symmetry, but you can't have a trans epoxide on that ring. There's no way to build that type of molecule. It has to be either from the top or the bottom for how that will react. Now this is kind of a key thing here. Trans alkenes go to trans epoxides. These methyl groups are still across from each other. Okay. Cis alkenes, similar to the ring one there, go to cis epoxides. Okay. Okay. This one's achiral. This one's actually chiral. Okay. This is generated as a DL pair. This one has the symmetry here, so that one we'd say is what, meso, right? Or achiral, but it's cis. That's referring to the two methyl groups there. So let's see, how can we come up with a mechanism here that accounts for these observations? Okay, so let's have our alkene here, and whatever we have on there. So we're looking at kind of a sideways view of the alkene, right? And now let's have the peracid here, and the electrophilic oxygen's actually this end one right here. Okay. So I'm drawing kind of a high energy conformation, but you could say we've got some hydrogen bonding going on up here, right? There's a lone pair here and a partially positive hydrogen there. So we're kind of invoking that. This mechanism is called the Bartlett mechanism, developed by Paul Bartlett at Harvard in the 1950s. It was the first time the mechanism accounted for all of the observations for epoxidation. It's been confirmed theoretically in a number of other experiments. This reaction I'm going to show you is the actual one. And it's stereospecific. The trans epoxide goes to trans alkene goes to trans epoxide, cis to cis. So how is this going to work? Let's push these electrons onto that oxygen. Now, what electrons are we talking about? The ones in the pi bond. Okay, I'm drawing out the whole pi bond here so you can see how these things go. And then we push these electrons up to here. We're breaking this really weak oxygen-oxygen bond, which should make some sense. And also what? The alkene is the nucleophile. Okay. Here's our electrophile. Okay, it wants these electrons in the pi bond to break this oxygen-oxygen bond, right? If we push the electrons up there, look, we can then bring this over here and grab this proton off the OH group. That then liberates these electrons to go down and fill in the empty orbital on the alkene. So let's see, what does that go to? It goes directly to the epoxide. Okay. And there's no intermediate. It's known to be what's called a concerted mechanism. It's just one step bimolecular reaction. When those two things collide with the right geometry, it goes directly to the epoxide. Well, what happened to the peracid? Well, it ends up as a what? Carboxylic acid. Okay. So the peroxy bond is gone, and you've got the peracid, and it goes directly to the alkene. I think that's all we need to say there. You could do it stepwise and see, but if you just did this step here and stop there, you'd actually have a carbocation here. And if you could rotate around that carbocation, you might scramble the stereochemistry. But it's known to be stereospecific. In one step, you can see what trans and cis go to trans and cis products directly. Okay, so the one step thing reinforces this idea right here. Questions on epoxidation? Okay, let's do dihydroxylation, which is going to be what, the osmium reaction. And if we do the osmium, we're going to do this, osmium tetroxide. There often has to be some water in there. The water can be in there from the beginning. We actually just have to have a proton source, okay? You'll see from the mechanism in a second here. What does it go to? It goes to the diol, okay? Both alcohols are incorporated for both carbons of the alkene there. Sometimes instead of using a full equivalent, we can use it catalytically and add in NMO. Yeah, yet another acronym. The problem is osmium tetroxide is very toxic. Okay, so industrially, if they're going to do this on ton scale, they'll use a tiny amount of catalytic of the osmium tetroxide and then have a stoichiometric amount of NMO, which is this guy, and morpholin and oxide, which is this material here. Okay. Looks kind of funny, but it's O minus N plus. And this is able to transfer this oxygen to the reduced form of osmium and regenerate osmium 8 in the tetroxide state, and that can keep the reaction going there. So NMO is cheap. It's very good to have that basis there. But for our class, if you just show osmium tetroxide, you're fine. Okay. Be aware of this. So, and let's see. So a couple of reactions here. How about this one? Same thing, osmium tetroxide. What are we going to get? The diol. There is a stereocenter, right? So it'll be DL at that point. Okay, and where is the stereocenter? Right there. Not out there. How about this one? So we have a double bond outside the ring. We'll get the diol right here. Okay, it's always where the alkene is, right? And if we've got this guy, same thing. What are we going to get? We're going to get the cis diol, okay? And again, that's going to be a consequence of the mechanism. The osmium tetroxide is going to lay down just on one face of the alkene, top or bottom. We'll give the cis geometry there. And you kind of see why the water is needed. We're going to have to protonate the osmium intermediate there, okay? Let's see if we can do a mechanism here, at least a little bit of it. So, and let's do the one with the ring there. So cyclohexene, and what do we have? The hydrogens pointing out at us here, and we'd have to have our osmium underneath here. Now there's a lot of O's floating around here, right? Verify that that is indeed osmium tetroxide. The heavy metals in the middle, right? OS. And then you got the osmium oxygen double bonds there. And it's the same thing here. The alkene is actually the nucleophile. The osmium is the electrophile. Well, why is that? Well, it's such a high oxidation state. Osmium's pulling on these electrons, okay? You can think of the metal as being electronegative to some extent. And let's see how the mechanism's going to work. Well, there's our attack, right? There's our nucleophile using the pi bond to attack. Well, what does that do? That pushes the electrons down into osmium. So if you just looked at that part, you'd say, okay, I can see the osmium gaining electrons, getting reduced, okay? And then this can liberate these electrons to go up from the same bottom face there to put the oxygen on that carbon. So let's see what that looks like. It'll have oxygen, oxygen, osmium, and these other two are still there. I put some electrons on osmium. Okay, these are d electrons. If you remember your d series of transition metals, d orbitals. We're not going to analyze all that, but you can see now we've got what 1, 2, 3, 4, 5, 6 lines to osmium. So we went from osmium in the 8 oxidation state, the most highly oxidized form of osmium, and we went down to what? Osmium 6. Now that's another way to keep track of the mechanisms, I think, because the alkene's getting oxidized, right? It's adding oxygen, and the metal's getting what? Reduced. It often goes together. But we've kept track of all the mass here, all the elements, right? Including electrons. So they're still there. We didn't destroy electrons. They're still there. And then what can occur at this point? Well, then you can kind of see what the water's all about. Actually, the water adds first to the osmium center. It forms an adduct, a hydronium ion, and then that hydronium ion can transfer a proton, okay? But you see these proton transfers occur on the oxygen. It doesn't bother the stereocenters, right? So these hydrogens here you see are up, the 2 oxygens are down, right? And that accounts for our observation. It's a cis style. So if you do that, you get to that, okay? And you get to osmium 6 still, okay? And that osmium 6 can go back to osmium tetroxide with what? NMO. And I'm not going to go through that. We could push electrons and show you how that works as well. But we'll just stop at that point, okay? The important thing is the organic reactivity and observing the stereochemistry of these products, okay? Questions on osmium, okay? Notice this is a complement to what? This is a complement to this reaction, which we learned before, right? What's that? That's the halohydrin reaction from chapter, 11 or 10? If we react this with sodium hydride, we can deprotonate here, and that can do the backside attack here and give the epoxide. Okay, well, we know how to do this reaction now instead of from the alkene, right? We know how to go directly to that with MCPBA. Now, why am I pointing this out, relating it to osmium? Well, we open up the epoxide with sodium hydroxide. There's our charged nucleophile, right? Backside attack. And what is it going to give? It's going to give the trans product, okay? Transdiol, whereas osmium directly gives the cis, okay? So it's good to keep track of these and relate it to previous reactions, what we've talked about. And this is also from this chapter 12, right? Forming the epoxide instead and opening it up to form a complementary diol. So that gives you a lot of power over that. All right, let's look at ozone. Ozonolysis. Ozone can be generated. The biggest use of commercial ozone nowadays is swimming pool disinfectant. Instead of using a lot of chlorine in swimming pools, they have these ozone generators that bubble the active oxygen through the pool. And it's actually less toxic. But ozone is a damaging material. It's considered a pollutant. It's also formed in the lower atmosphere from cars and other industrial processes. So ozone is kind of a tricky reagent here. But what is it? It's oxygen, oxygen, oxygen. And oh, yeah, it's got resonance stability to it. It's a bent molecule, O3. You probably played around with it in Gen Chem, drawing the Lewis dot thing. It is electrophilic. It's going to be highly reactive here. It's going to form an intermediate here. And we'll push electrons. You'll see how that can form. And this can actually rearrange to another intermediate here. These are called ozonides. We don't isolate these. In fact, these are detonation hazards. These can explode, okay? This is 3 oxygens, a trioxide, and those are weak bonds, so that can convert to CO and CO2 very quickly, so it's a detonation hazard. But we work it up with dimethyl sulfide or zinc, something that has electrons, and then we'll get to the carbonyls. In this case, it would be 2 formaldehyde products, okay, from ethylene. Depends on what's on the alkene, how the aldehyde or ketone ends up, okay. But yeah, so let's see, let's do a couple reactions here. How about this one? O3 here would give us 2 what? Aldehydes, right? And molecular scissors, that's what we're talking about, right? We're breaking the pi bond and we're breaking the sigma bond. That's unique. We haven't done that before. We've always said sigma bonds are very stable. Indeed, they are, about 90 kcals per mole. So this is a very powerful oxidant, okay? You can kind of smell it after a rainstorm or a thunderstorm sometime. Maybe you've heard about that kind of pungent, acrid smell you can smell in the rain sometimes. That's ozone, okay? We form it in the lab from oxygen and an electric arc, okay? So there's 2 metal leads, and you pass a strong electrical field across there, and then you stream the oxygen through that electrical arc, and it'll form the O3, okay? So it's a high energy molecule, but yeah, so this is a product there. How about this one? If we do that one, we'll go to the ketone plus formaldehyde, okay? And let's see, if we move the alkene inside the ring here, what about that one? Now, you know, there's a tether here between the 2 pi bond carbons, right? So we're going to get ketone up here on one side, and then the tether comes around, and what? We have the aldehyde over there. So it depends on where it is, and you know, just do the molecular scissors idea here, and you'll always come up with the right product. But it kind of can be kind of tricky to see sometimes. Okay, let's do the mechanism here and see what we need to know there. Not much. It's pretty simple. Oh, let me redraw this right on our alkene. So again, the alkene's the nucleophile. Ozone is the electrophile. So the initial step is what? These electrons coming out, pushing here, and what? If this came out, then this can just come here. Does that lead directly to this ozonide? That's called the primary ozonide, by the way. That's okay. We can break this apart by taking these electrons here, and let's see, I always mess this up. Let's see. Need to bring these electrons here. Bring these here, and this one here. Yeah, okay. And that will go to see the formaldehyde right there, O minus right there, and O like that. Okay. And then I think you can see you can just turn this guy around, and that will give you this. Yeah, okay. And then, yeah, you see we just flip this over to this, and then this can come in here, this can go in there, and that goes to this, to the secondary ozonide, it's called. And let's see, the secondary ozonide, let's see, do we want to finish the mechanism? I guess we can here. Dimethyl sulfide can attack there. And by doing that, you see we can break this bond here. So we'll go to this. Yeah, that looks kind of funny, right? And then what? We can bring this here. Yep, and that will give us that. Oh, Yeah, and that gives us that. Believe it or not, that flow of electrons gives you the two carbonyls. There's one carbonyl right there, and then there's that one right there. And then what does sulfur end up as? Oh, it ends up as DMSO, which is the byproduct, dimethyl sulfoxide. DMSO is a solvent. So the sulfur ends up with that extra oxygen, and then you just have the two carbonyls, but they're not connected anymore, right? So they're either aldehydes or ketones. By the way, I've never put this part of the mechanism on a quiz or a test, but it's an awareness issue. You need to understand that there's another reagent that should be added here. If you leave it off, we'll probably give you full credit, but the ozonide can actually be stable enough to be a problem there if you don't break it down. Okay, let's look at a couple other substrates here. That mechanism's a little too much. What are some other ones here? How about this one? So these are very useful reactions, right? Because this will go to a dialdehyde. Okay, and when you're thinking about functionalizing things and making different products, if you can cleave this right here, okay, that makes a highly functionalized 5-carbon unit with 2 aldehydes on it. Okay, very, very important transformation industrially to be able to convert aldehydes into other type of highly functionalized things. What if we have something that has maybe multiple double bonds on it? This is actually a terpene. This is called limonene in citrus fruits. If you take limonene here and treat it with excess ozone, and again, it's a small gas molecule. It's very difficult to control it and have one equivalent. It's always in excess, even if we don't show it there. So what do we get here? Well, that becomes a ketone up top there, right? This becomes a ketone down here. And what? This becomes an aldehyde over here. And what happened to this carbon up here? Well, that's formaldehyde, right? The simplest type of aldehyde. So how many, well, we cleave here and here. And you see that'll generate a ketone right there. Okay. And then this methylene here will become what? Formaldehyde. And then this right here becomes a ketone. That's a methyl group right there. So it's a ketone there, methyl ketone. And then what? This is an aldehyde right here. So sometimes it's important to draw in the hydrogens there to keep track of what's what. But these more complicated examples can be useful there. All right, what about alkynes? Alkynes also react with ozone. They react a little bit more slowly. Sometimes water has to be added here to protonate. What's the product? Well, it's actually carboxylic acid. Okay, both of these become carboxylic acids. I think this one, yeah, has 3 carbons on it. This one has 4, so it's right here, breaking what? 2 pi bonds and the sigma bond in the middle. Now you can go through the mechanism there. It's a little bit more complicated. You actually have 2 ozonides they have to break down, but then that gets fully oxidized there, which is our last topic, the alcohol oxidations. And if we take the alcohols and think about oxidizing those, it looks like this. So here's a primary alcohol, and let's look at a secondary alcohol. And oh, let's throw in tertiary. Okay. So alcohol oxidation. So they're already oxidized. They already have an oxygen, but there are functional groups that are more oxidized, right? Aldehydes and carboxylic acids. So what can we do here? Well, if we take chromic acid, and remember, we can form that either from the chromate salt and sulfuric acid or dichromate salt and sulfuric acid. And if we do that, we'll get what? Carboxylic acid. Okay. The carbon has to be on the end to become a carboxylic acid with the oxygen to begin with, right? And there's 2 hydrogens here that are removed. So remember, oxidation involves adding oxygen, which you see, extra oxygen, and taking off those 2 hydrogens. Okay, so oxidation to the acid. Okay. If it's secondary here, same reagent, it'll stop at the ketone. Okay. Now that comes out of the structure, right? You only have one hydrogen here now on a secondary, right? So if you take that hydrogen off and form the pi bond there, you get the ketone. Now that holds for chromic acid or PCC, okay? Now if you use PCC with the primary there, you stop at the aldehyde, okay? So PCC is a little more versatile. It's more expensive. It's easier to work with. We like it, okay, on small scale. It's great because we can then do the aldehyde or the ketone. But if we want the carboxylic acid, then we use the higher oxidation state, the acidic form, and go to the carboxylic acid. Now, what about tertiary? Any of these reagents with tertiary, notice there's no hydrogen on here. So there's nothing to pull off, and you'll see from a little bit of the mechanism we're going to do, we get no reaction here. Okay, let's put a little bit of the mechanism up here and look at this just to get a little better feel for this. I'm not holding you to the mechanism, but let's look at the one here, the secondary alcohol with chromic acid. Okay, so the oxygen is actually a nucleophile. The reagent is actually electrophilic, at least this initial step. And what we'll get to is this. We'll have the chromium. We have to lose a proton here and lose water off here. I'm not showing that. So there's a couple more steps here. But I'm showing you this intermediate right here. That's called a chromate ester. And this chromate ester has a chromium carbonyl bond, you could say. So it kind of looks like an oxygen ester, you know, the ester functional group we've seen before. But it's got the single bond to oxygen also. So that's why it's called that. How does this work then? Well, you've got this hydrogen we need to pull off. This is secondary. And this mechanism holds for primary as well. But you can see if this was tertiary, we wouldn't have this hydrogen right here, okay? That hydrogen actually is acidic enough for water or another weak base to pull that off. And if we pull that off, these electrons then can flow into chromium. So you can see there, we did the osmium thing where we flowed electrons into osmium. Here we're flowing the electrons in there from this chromate ester. And what does this go to? It goes directly to the ketone product. There it is. And what? The chromium is now in a lower oxidation state. Okay? So I went from chromium 6 to chromium 5 here. And it can keep going down here to chromium 3 or 4. And that's your bluish green color, actually. The initial higher oxidation state chromium is this bright red color, and that's the breathalyzer test. But you can see the oxidation there, part of the mechanism. And we do have a minute. Let me show you the mechanism here of NAD+. And I'm going to do NAD+ with a primary alcohol, ethanol. NAD, this is a cofactor in an enzyme reaction called a dehydrogenase. This is going to take off hydrogens and do the oxidation to the aldehyde, acid aldehyde from ethanol, okay? So how does this work? Well, NAD plus is this. It's nicotinamide adenine dinucleotide. Nicotinamide is related to nicotine, by the way. There's a big thing down here that has adenosine and a dinucleotide. We're not looking at that. This is just the business end of NAD+. How does NAD+ convert an alcohol into the oxidized aldehyde product? Okay, well, it does this. It has an enzyme here. This enzyme actually has a basic side chain, which is usually a histidine, okay? There's an amine base there inside the enzyme. And the enzyme is going to take this proton off the alcohol, okay? And it's going to flow these electrons in here. And, you know, this is a primary alcohol, so we have hydrogens right here. These hydrogens can flow into the pyridinium cofactor and push these electrons, what? Onto the nitrogen, which had a plus charge to begin with. That's why it's called NAD+. It's a pyridinium plus charge, okay? But let's see the result. Well, if we take that proton off, our enzyme gets protonated, okay? And what happened? Well, there's our substrate. We took one of these hydrogens right here. Let's circle that one. Where'd that one end up? It ends up on the nicotinamide. Okay, has an amide there. And look, this hydrogen right here that was circled ends up right there. Okay. So we took the hydrogen with its electrons, this movement of electrons, we what? Reduced the NAD+. This is now NAD what? NADH. You've probably seen that cofactor too. That has the hydrogen on the pyridine still, okay? In fact, this is reversible. You can go back to the aldehyde with the same substrate and the same enzyme. But if you've drunk a lot of alcohol and you have a lot of this, and this is also pertinent to yeast, okay, does the same thing for fermentation. But flowing the electrons there gives the hydrogen there, and yeah, we're over time. Anyway, this is Mother Nature's oxidizing agent. It gets reduced in what the substrate got oxidized, okay? You'll learn more about that in biochem, but it relates to what we just talked about there. We'll start 13 on Wednesday. I'll show you a little bit about the asymmetric epoxidation. We don't have time to do that, the sharpless thing. You don't need to memorize which enantiomeric form of that catalyst goes to which enantiomeric form of the epoxide. You just need to know that it is chiral asymmetric. I'll show you some examples of it. So very good. We'll see you on Wednesday. Thank you.